Good afternoon, everybody. Our Nirmala auntie told us that it is the hand of God which determines many things. I was supposed to talk first, and fortunately for me, I was delayed by Indigo flight. And thanks to Chakravarti, she has taken over the first this one talk. Okay. Now, whatever I am going to talk to you today is not completely about my research or research. Okay, it's a popular talk so that students and teachers will be motivated towards doing some chemistry at least. That is the reason why I have chosen this particular topic. Only the last slide shows something about what research I am going to have been doing, and I am going to do in future if there is if there are enough facilities. Okay, the topic that I have chosen is serendipity in chemistry, Prussian blue and Ferrocene. Okay, with inputs on coordination and organometallic chemistry. Okay, the main compounds that I am going to talk about are this one. Okay, that is Prussian blue and Ferrocene. In the periodic table, you know where iron comes. Okay, this is another way in which you can represent the periodic table. I'm not going to the details of that one, but then we'll straight away go to. I'm going to tell you what about the things about serendipity as such. The word was coined by some Walpole, and the origin is the Arabic name of for Sri Lanka. So Serendip means land of lions. Okay. Now what happened long back was that three princes of Serendip, it's a fairy tale sent by their father to explore the world. They were always making discoveries by accidents and by sagacity of things they were not in quest of. Okay. But then when they were going along, when they were just walking, a camel driver stopped them on the road and asked if they had accidentally seen one of his large camels. Now, the way in which they were trying to answer this question is like this. Those princes asked him, was the animal blind on his one eye? Was it lame in his one leg? Was he loaded with honey on one side and with oil on the other? These are the questions which they asked. That's how they probe and they find out how it is. But then they did not anticipate that the camel driver was coming along the way. Okay. But now, why did they ask these questions? Because they noticed these things. Okay, the grass was eaten only on one side of the footpath. Okay, that answered the first, this one. Where is that? Loaded with honey on one side. Okay, this one, animal blind on his one eye. That is the answer to the first question. The second, ants loving fat buzzard on right side of the road. That is the answer to the second question. And then third one, with oil on the other, bees and other insects flitted on the left side. This is the observation which they made. Now, many of us do experiments. It's not just in chemistry or any branch of science. You do experiment, but what could happen is that something which is not expected could happen. The only thing that we have to take care of is the way in which we observe that kind of a thing, the way in which we analyze that kind of a thing. That is what is important. That's what these princes were trying to do. Now, sorry about my English and all that. My English is not that great. For that reason, I just thought that I'll put this slide. This was a notice which was put in Chennai airport sometime back in 2019 or so. It was advertised in this one, NDTV. You see that eating carpet is strictly prohibited. This was shown there. Actually, what it meant was that eating on the carpet is strictly prohibited. Okay, this is just to show that sometimes we make mistakes in English. Just excuse me if I make any mistake in English. Okay. Now, what is this Prussian blue? This Prussian blue is a color that changed the artist's world. Okay, I have a sample of this one somewhere there. Okay, the color that changed the artist's world. The reason why this became so popular is because during the 17th century or before that one, people didn't have access to a good blue color. Okay, the thing that they were using was the ultramarines. They had to get it from Afghanistan and other places. Okay, but then it was really very, very expensive. So people were in the lookout for a good blue colored pigment. And this particular pigment satisfied all those needs. This is what I mentioned to you. Mentioned here. Note this Egyptian blue were there. Okay, this is this also silicate. Ultramarine also is a silicate that's generally found in Afghanistan, and then indigo is there. Indigo is not suitable for many purposes. Okay. Now, it is also said in some references that the Prussian army during the 18th century uniform, they had this one Prussian blue on this one, but that is not true. It's probably indigo. But then in World War II, there was some use of this Prussian blue. German spies wrote secret words on their socks and clothes buttons when sprayed with the ferrocyanide. Okay, ferricyanide is there, and then when they spray with the ferrocyanide, then letters called ferric sulfate reveal themselves in blue lines. That's Prussian blue or turnless blue. Actually, both of them have the same structure. Okay. Now, what is the origin of this particular pigment, which really fascinated so many artists around the world, and then for a large number of artwork also, this was really very, very important. There were two people mainly involved in this particular type of work. These are this Dippel and Jespa. Okay, and there is also another person, Gestal, who is famous for the Pakistan theory, and theory, and then Dippel version. There were different versions, but then the two people who were mainly responsible for this pigment, which was very, very widely used in the 18th and 19th century, were Dippel and Jespa. That is what the story about that is what I am going to tell you in the next several slides. Now, this Dippel, okay, was an alchemist and a radical theologist. Many times he was jailed, okay, and then he was working in Berlin laboratory during 18th century, 1704 to 1707. Now, one thing that you should note here is that your even elemental nitrogen and many other elements were discovered much later. So these people didn't know what actually they were, they were doing as far as the chemistry part is concerned. So they were trying to mix certain things, but then in serendipitously they got this particular pigment. Okay, and then what he wanted to do was to find a universal medicine from the so-called animal oil. Okay, which was produced through distillation of animal or ox blood. Okay, don't feel too bad about it, but that is the case. Okay, blood to which potassium carbonate had been added, and that used to, obviously you know that will give disgusting smell. And what are the types of compounds that it generated? Pyrroles, pyridines, nitriles. Nitriles are very important here. Okay, now, on one particular occasion, what happened was that there was a wrong label by his assistant, lab assistant. Many times you might have noticed, or if you are a teacher, you may notice that your lab assistant will mix or will give one compound for the other, and all those things will happen. Okay, such a thing had happened here. What happened was that there was a wrong label by his assistant. He wrote it as salt tartary, that is potash. Okay, potash is fine, but then he just wrote it. But the thing that he did not mention is it is from the waste material which was collected before. And then there is another person, the second person I am talking about, that he was a color maker, and he was in Swiss national working in the same laboratory around 1706 AD. Okay, this is between 1706 and 04 and 07. Now, what this person wanted to do was to get a red pigment. Okay, this Florental lake, that's what is called, red dye carbonic acid. That's the compound, the name of the compound, from crushed insects. Okay, in heated aqueous alum. Alum is potassium aluminum sulfate. Okay, to the filtrate, potash solution had to be added. So he needed the potash solution. Okay, to get the red carbonic acid. This was a paint in which this particular person was interested, and he used to get this one on precipitated alumina. Then what happened? Now this is the full schematic of that particular process. Okay, arms, bones, dyes, blood, all those things, destructive distillation, and then crude animal oil, multiple distillation, again distilled animal oil, multiple distillation over potash. Okay, that's purified animal oil, multiple distillation. This is the Dippel's oil, the first person's Dippel's oil. But then this, he used to sell and saying that it's some kind of amrita or something like that. Okay, it's elixir weighted, that's what he used to call, and then he made a lot of money by selling this one. Many distillations of the crude animal oil partially over potassium carbonate and burnt light. Okay, it was a really commercial success. But then what happened there? The other person, about the other person I'm telling you now, the other person was using this instance to get this carbonic acid, which is red pigment. Okay, and that process is like this. Okay, that I'm not going to tell you anything about this one. He was using alum insects he was using, but you notice that he was using potash at some stage. Now, he used to get carmine red Florentine light, red one, and purple colored material also used to get. But in both the cases, he was using potash. Now, what happened at a certain stage was that this Diepel was doing all these things. That's what I told you a couple of slides back. And then this Roser, which was the lab assistant, what he did was, there was the residue over there. That residue he labeled it as Roser's potash. Okay, that was the thing that he did. But then this particular person, what happened on a particular day, he didn't have enough of this potash. So what he did, he took this potash. Okay, Roser's potash. Okay, and then he added that one to whatever he was trying to do. Then the next morning, what they observed was this Prussian blue, which is a really dark, this one, blue pigment, okay, which became really very famous towards 18th century, as I told you before. So by the next day, he got this one, because there was so much of scarcity for low-cost blue pigments during that time. Okay, they were able to sell this one. Okay, now this is the story about how the serendipitous discovery of Prussian blue was made. But the problem there is that this Roser, okay, he was his potash got exhausted on a particular day, and then what happened for this bar? He ran out of the potash that was collected by the lab assistant. Then he borrowed some more from Diepel. Okay, he also had potash, but then the problem there is that this particular thing, first time it appeared at all that's fine, but then after some time he ran out of potash, but ordinary potash won't work. Okay, initially what he did was to use the potash which was the residue from Diepel. Okay, residue from the animal oil and all that, which contains iron. Remember, that contains iron. Okay, but next time, once that got exhausted, he wanted to have this potash, but then what potash that he used that got exhausted, and now he has to use the normal potash. When you use the normal potash, it so happened that the ordinary potash won't work for that one. The reason being that, as I mentioned before in one of the earlier slides, the cyanide was liberated earlier. Okay, that cyanide from the animal blood or crucible that with potash. Potash contains potassium, and that will form potassium ferrocyanide, and this will get oxidized by air. And then the color, it's a mixed, about the chemistry I will tell you a little bit later. Okay, but then he contacted many people for this one, but then the normal potash will not work. Then he requested Diepel sir. Diepel lab is where he was working. Okay, then what happened was that the calcination of potash with the dried blood, that's what they try to use now. Now what happened, alkaline solution with cyanide and hexacyanoferrate to the acidic solution of carminic acid. Okay, and iron too. Actually, carminic acid is not required. They did not know the actual chemistry over there. Iron too. Then they had the colorless ferrocyanide. This is the ferrocyanide. Okay, that got precipitated, but then it slowly oxidized by air to the deep blue, iron 3 hexacyanoferrate 2. Okay, this particular compound has both iron 2 and iron 3, two oxidation states. And that is the Prussian blue. So they got hold of a procedure by which they could get this pigment. Okay, and now because as I told you, because of the scarcity of blue pigment, they made huge amounts of money. Some of the arts I am showing you later on, artists struggle to find an inexpensive, stable, brilliant blue pigment. That's indigo. There was a problem with that one. Okay, I will not tell you about that. Azurite, all those, the ultramarine, and this is one of the things which they had to import. And this lapis lazuli, many of them are silicates.
But then afterwards, there was a problem. This people, as I told you before, he was a theologist. Then he used to give sermons and all that, and that was not liked by the king. And therefore, what happened? He was arrested for publishing the books against the Swedish king. Okay, hence to another, he has to be. He was deported to he had to go to Netherlands and produce some Prussian blue, but then not so much. He was imprisoned. So the whole thing stopped over there. But then this other person, the person who was making the pigment, that Disba, he met his teacher Frisch, okay, and they came to an agreement, and these two people, what can I say, knew now how to make a large amount of Prussian blue, and they called it as Berliner blue. Okay, that is the same as Prussian blue, and they made huge amount of money by that. But then that secret was not out at that time. Now there was another person who knew about something about this one, okay, and this Frisch or somebody, okay, they anonymously sent this details of this secret, how to make this and all that, okay, to this one, to this Neumann. He was a friend of Frisch, okay. This Frisch transferred his knowledge to Neumann, okay, and then this Neumann sent an anonymous letter to Woodward, okay. This Woodward, what he did was, okay, he knew that something is working. He asked one of his colleagues to prepare that one. I think it is Jeffrey, okay, prepare that one, and they knew that that kind of a thing does work, and that pigment can be prepared very readily in large quantities. But then he published that one in the philosophical transactions of the Royal Society. But then this person wrote the letter, but it was an anonymous letter, okay, and therefore the publication was there without the name of the author, okay, without the name of the author. But then that was in 1724. Now everybody knew how to prepare that one, how to manufacture this one. But you notice that here, whatever you have to do is to kill the animals or take the blood and all that. This is so tedious, okay. But still, the people who made the pigment got lot of money out of this one. Now the recipe is revealed. That's what I am trying to tell you. Okay. Now you see that this is dried cow's blood or ox blood. Okay. Then you have to add potash, bring to ready. Okay. This is the procedure. Procedure is fine. Only thing is that they did not know the chemistry. And then blood this one leachate. Okay. That mixed with alum or iron, which alum is not required there. That they did not know. Iron vitriol solution to the mix. They get a green precipitate. Okay. And then filtration. Pour hydrochloric acid over that one, and then over a period of 24 hours or something like that, they get that recipe was revealed. Okay. Now they got the Prussian blue. That is fine now. Now which are the places wherein you can get iron? Because now we know that we need iron for this one. How you can get the iron over there, and that also they didn't know that iron was required at that time, but now they found out that that is required. And then gas purifying mass of the coal gas and coke production, in that one iron compounds were used to eliminate hydrogen cyanide from the coal gas by formation of hexacyanoferrate. Okay, that they tried to get that one like that. And then there was another process from methane and ammonia. This cyanide reacted with iron 2 to give hexacyanoferrate. The gist of whatever I am showing you here is to show that they have other sources of iron by which they can get the Prussian blue. Now this is Prussian blue. That is the color of that one. That first slide is there. Now this is a very famous painting. Okay, art Vincent van Loo, the Starry Night, very famous one. And this is the other one, a Japanese person. Okay, Hokusai. Okay, Great Wave of Kanagawa. If you look at if you just Google it, all these things will come very readily. These two are really very famous paintings. Okay. And then this one, Elizabeth Louis, this is this lady, Teresa, Countess Kinsey. This is another one. This blue thing is from the Prussian blue. And then unused blue 2 pence Mauritius stamp, 1847. Now it's worth millions. Okay. I hope that I had it, but then I don't have it though. Okay. But then Crown Jewel of Philately, it's worth billions. Okay. Now this is about the Prussian blue. You can also have green color and other colors if you have other elements or other metals over there. Green color, if you want to have the green color, mix Prussian blue and chrome yellow to depict a green garden sea. Now, overall there are different stories as far as the discovery of this Prussian blue is concerned, but there is we have to come to a sort of conclusion. Overall, they say that it is around 1706 it was discovered. Okay, but then now, as I told you before, not much chemistry was known at that time. Okay, in 1771, Scheele found out about elemental nitrogen. This is 1771. You notice that this is in 1706, and then 1806 John Dalton hypothesis of the atom. Okay, 1807 Humphrey Davy potassium from molten potash. So they didn't know the actual elements which were involved involved in that particular process. And then 1782 Scheele and Gay-Lussac, they got the acid prussic. Okay, that is the blue acid or cyanogen. This they obtained by the acidification of Prussian blue. Whatever you are talking about, whatever this hydrogen cyanide that you know of, that is that started from Prussian blue. Okay, and earlier it was called as prussic acid. Okay, now calcination of dried beef blood, okay, that contains protein, about 14% nitrogen, together with potash gives cyanic acid, formed when enough energy is added to substance, because they were heating it to really high temperatures, okay, containing carbon, hydrogen and nitrogen. Organic chemists should be happy about it. Happy or unhappy, I do not know about it, because KCN is something which nobody likes though. Okay. Now, the reaction is like this. HCN is produced. That HCN reacts with K2CO3 to give rise to potassium cyanide. Okay, potassium cyanide reacts with plus potash. That is the Rosel's dipples this potash. Okay, that was the that is the chemistry of that potash that they were using initially. And then overall reaction is shown here. Potassium cyanide is there. Now, with iron 2 plus, you get potassium ferrocyanide. Okay, yellow prussiate on the potassium ferrocyanide, and then with again some more Fe2 plus, you get this one. This is not that dark colored. Okay, this is not the colored one. Or otherwise, you can add Fe3 to the if you oxidize that one to Fe3 plus, and then you combine that with the ferrocyanide. This is Fe3 plus and this is Fe2 plus. If you add that one, you get the Prussian blue. Here you have got both of them in Fe2, then one partial oxidation will give rise to Prussian blue. Okay, Fe2 to Fe3 partly, or Fe3 to Fe2 partly. Okay, one is called Prussian blue, other is called turbulence blue. As far as structure is concerned, both are essentially the same. Okay, now that is Prussian blue, and this is the insoluble version of that one. This is the soluble version of that one. Okay, both of them contain Fe3 as well as Fe2. Okay. Now, you can also hydrolyze those things. Okay. If you hydrolyze, you get HCN over there, or if you in the basic condition, you can get this ferrocyanide comes out and ferric hydroxide will precipitate out from that. Okay. Now, these are the things that you should know, and in this particular process, you also know that should know that HCN is being involved. Now, this HCN is really very, very dangerous. Okay. I don't know how many of you know about this particular Holocaust. Okay, here HCN was used to kill about 1.1 million people in Poland. Okay, that is, if you look at the Google, you can see that one. Okay, that HCN, the origin of that HCN is the Prussian blue actually. Now, as I told you before, these two have the same structure. The way in which you get the two pigments is Fe2 plus 2, Fe2 plus, you add that to ferricyanide, or that is Turnbull's one, and Fe3 plus 2 ferrocyanide, that is Prussian blue. Okay, that is the point that you have to, that is the normal thing. Okay, that's how we know about it now. It's so easy. Now, after knowing all these things, it looks as though the chemistry was so simple. Okay, but at that time they did not know about this one. Now, this is the other way by which you can write the structure. This is ferrocyanide. You see that is connected to carbon. Okay, that Fe3 plus is outside. Now, overall structure looks like this. Its soluble Prussian blue is blue, and then mu max is given there. Fe3 plus is high spin. This is for those people who teach the inorganic chemistry. High spin D5, Fe2 plus is low spin D6. Now, what happens in the structure is that Fe2 plus is connected to, this is Fe2 plus is connected to carbon end, and in the overall structure Fe3 plus is connected to the nitrogen. That satisfies our hard and soft acid and bases concept, okay, that most of you know about. The blue color, why does the blue color arise? Blue color arises because of the charge transfer between Fe2 and Fe3. Now, this is the structure, okay. I told you about that one. Fe2 is the red, okay. The red one, okay, is connected to the carbon, and carbon is this one green, okay. Fe3 is blue, okay. That is connected to the nitrogen end of that one. Nitrogen is red, okay. So, that is the overall structure that we came to know much later than what when it was produced. Now, at least the older generation know something about the so called blueprint, okay. Blueprint is a part of the story as far as the Prussian blue or Turnbull's blue is concerned, okay. It is something like what you have in Xerox now, okay. Earlier days, to make a photocopy of things, what they used to use was something, this one, the first thing that they used was to get the blueprint or cyanotype, 1840 to 1940. That is also an accidental discovery or serendipitous discovery, okay. This person in 1842, first ever industrial photocopying process, multiple versions of the original, I mean, okay. Using Prussian blue or the Turnbull's blue, okay. Useful for architects, okay. I don't know how many of you are that old. I think only older generation will know about it, okay. Anybody older than me, more than 70 years? Nobody, okay. Earlier generation will not know about it, okay. Only I think he will know about it. All right. The name is derived from this one, blueprint is that. Now, what they used to do was, okay, the paper is coated with potassium ferricyanide, okay, and this one ammonium iron 3, okay, iron 3 citrate. This is citrate. Both are soluble. The second one, what happens, undergoes photo reduction of Fe3 under UV light and reacts. And then what you have to do is hold a black ink sketch drawn on tracing paper or photosensitive paper and expose them both to light source. This is the first Xeroxing, so to say, okay. Parts that are not protected by dark blue lines, okay, will change their chemical formulas in the light. Or not protected, what will happen? There you get the Prussian blue or the Turnbull's blue. Would change their chemical formula and the light, and from ammonium ferric citrate to ammonium ferrous citrate. Then Fe2, this is Fe2, it has become Fe2, okay. Then Fe2 you have got the here, and then that will react with ferricyanide, okay, to get white sketch, okay, like this, white sketch on blue paper. It is light stable, now familiar term blueprint, okay. Many times you use this term blueprint, but then that arose because of that. Prussian blue was also, this is just an addition, that's all. It was also called as the molecule, it was the molecule of the year in 2017. Now, how many of you recognize this one? Anybody recognizes this one? Blueprint, okay. Earlier days people used to have this kind of a thing. The reaction is this one, reaction I have given you there, per Prussian or Turnbull's blue, okay. That is the kind of sketch which people used to make for making the drawings of the buildings they are going to construct and all that. Now, this also, there is also a possibility that you can have the smart windows using this Prussian blue, but then the ones which are currently being used are not from the Prussian blue, okay. They are from a different source, okay. The more common is the tungsten, this one tungsten trioxide, halogen, etc. But then this also can be used as switchable windows, okay. And then original crayon color and other things, the people were using this Prussian blue, and this also still it is used in pathology tests for bone marrow and all those things, thermal cancer treatments and all that. And the other major use here is antidote. It's an antidote for heavy metal poisoning. You may remember something about Saddam Hussein, and then radioactive cesium. You may remember something about Brazil accident and Chernobyl accident at all. And in such cases, okay, this Prussian blue can be utilized. Take out the, what can I say, radioactive material, okay. and histopathy stain for detecting iron, Prussian blue batteries, lot of work is going on there, and then Pearl's Prussian blue stain 1867 it was there for the detection of iron in tissue. Some of these things are still being used, okay. And then towards single molecule magnets, that's another paper, and there is an extension also of these things. Now it is not necessary that you need to have iron 2 and iron 3. You can have other transition metals. When you have other transition metals, you can have lot of other different colors and all that. That also has been investigated really thoroughly, okay. And then there are this is from my colleague Radhakrishnan, that's why I just put that one there. Lot of other people also have done that, okay. And but then there is also a dark side to the story of this one, HCN and all that. HCN is just hydrogen cyanide, which originally got from the Prussian blue and all that. There's bitter almond smell is there, the speech beads were used in judicial executions, okay, as far as back as ancient Egyptians, okay. Ancient Romans used to use the cherry laurel leaves as an execution method, cherry death. And what was the possible ingredient? That was cyanide over there, okay, in all those things. That where did the cyanide come? Originally from the Prussian blue and all, okay. And this Scheele, I think most of you have heard of this person's name. He mixed Prussian blue with dilute sulfuric acid, okay. He was able to produce a new gas that was colorless, water soluble and acidic. We now know that this gas was is hydrogen cyanide, as I told you before, okay. It is called this one dark blue, or the Blausara, okay, or prussic acid. Only thing is that don't try to do that one, because this acid is really very poisonous, okay. Although Prussian blue is not poison at all, but this is poisonous, okay. And then this one in England also something had happened there on 1845. A neighbor found Sarah means this lady, okay. She essentially died, but then the attending doctor had followed the man. There was a man along with her, okay. And then this man, what he did was to give her this one cyanide, and then he he just left. But then earlier days, you didn't have this WhatsApp and other things, okay. They sent this electric paragraph, and finally they could catch hold of that person. And the story is that this lady was killed by means of that kind of a cyanide which originated from that one. He had purchased a bottle of prussic acid shortly before he visited, and so they were able to catch him, okay. And I told you about the gas chamber in the Second World War and all that. And then G.N. Lewis, it is said that there was some problem as far as this one is concerned. This hydrogen cyanide might have been responsible for the problem associated with his death. Now the references are here. I don't know how much time do you have? 5 minutes, 10 minutes? 2-3 minutes. I see, okay, that is fine. So then I will not go too much to the Ferrocene story, okay. And you see that these are the ones. The two things I have already shown you, and this another one, Prussian blue type nanoparticles and nanocomposites. And then the third one is, this is that lady Anna Atkins, 1843, okay. This is how she got a lot of them really printed. It looks as though it is really real, okay. Now this is purely chemistry. Now the reason why I chose this one is because after this ferrocene was discovered, the so-called organometallic chemistry flourished like hell, okay. But then before ferrocene was discovered, then also large number of organometallic compounds were there, but then that did not that kind of a literature did not provoke people to go for too much of work, scientific work or chemistry as far as the organometallic chemistry is concerned. Now the reason why I chose this one is because people were interested in this particular compound, fulvalene, okay. It was predicted to be aromatic, okay. And therefore what this Pausen and Keeley did, they were doubtful about that one. They were trying to prepare this one and then oxidize this one, because ferric chloride can act as an oxidizing agent. This is what they do. That was their logic. They wanted to prepare that one, okay. Then what happened was that they got a product which was orange solid, and all the properties are given here, Okay, the reasoning I told you just now, ferric chloride will be okay, initial reduction of FeCl3 and then followed by the reaction and all that. This was accidental. They did not anticipate this particular thing, this particular type of reaction over there. But then the credit goes to this Prussian because his paper got published. But then before his paper got published, okay, these people had submitted the paper. Okay, they had this compound before, they submitted the paper, but then the publication became late over there. But then even before Prussian is the one who is being credited for the isolation of ferrocene. But now there were workers in Union Carbide, okay, they had some yellow sludge. They were just passing iron through this cyclopentadiene. They had yellow sludge, and then that was blocking the flow of the gases, and they didn't know what to do with that. Therefore, they just discarded that one, but they collected that one in a container or something. They had that one. Okay, but then the original, the first literature appeared here, although the submission by these people was done much before that one. Now, there is a lot of story about the Ferrocene also. Prussian I told you, he was a refugee from UK, and then the thing is that in Ferrocene, if you look at the structure, it is a sandwich type of structure. Okay, about the proposal of that particular structure, there was a fight as far as with the Nobel Committee which involved Woodward also. Okay, Woodward, and then the structure was proposed by Woodward, and then Wilkinson should be there. Wilkinson is there, and then Fisher. Prussian attended some meeting, but then in that meeting, okay, somebody told him about this one. There is a possibility like that, but this can be verified by using magnetic susceptibility and all that. This is something which happens to most of us, because sometimes we are ignorant about certain parts of chemistry or certain parts of science, and then what will we ignore that one, and we will not know that we have missed a really great chance like that. And Prussian missed that one. Somebody told him, but then he missed that one. But the type of structure, that is the Ferrocene structure, was proposed by Woodward, and Fisher also found out that one. Okay, they said Doppelkugel, and Woodward and Rosenblum. Okay, they proposed structure based on the magnetic susceptibility. At that time there was no NMR. Okay, magnetic susceptibility IR 1 CH stretch and dipole moment 0. Okay, that's how this one. But then here is the story about this one. When you want me to stop, you stop me, no problem at all. Okay, but then the story is like this. When Nobel Prize was announced, and Nobel Prize was given to not given to Woodward, it was given to Wilkinson as well as Fisher for developing the organometallic chemistry. But then Woodward wrote to the Nobel Committee, okay, saying that I was the first to propose the sandwich structure for these things and all that. Okay, he said that one, he essentially tried to fight with them. Okay, saying that I should also have been given the Nobel Prize for this one. He already had got the Nobel Prize, but then this also was, he proposed, there is no doubt about it, that they didn't bother about that one. They said that, I don't know whether they answered that one or not. Okay, but then he did propose that one along with Wilkinson. Okay, but there was a problem of that type. Okay, now the original structure that was proposed is like this. But then the actual structure which was finally proposed by Wilkinson, Woodward and Fisher was this one. Now, how did this one Prussian miss that one? What he did was, he had the crystals. There was another scientist to whom he gave the samples, but then that scientist was going around. I think it's Jacobson. He was just going around, so the structure was not done by him, and his sample was not investigated further. But then these two people, Wilkinson as well as Woodward, got to know of it. Woodward proposed the structure based on the IR, single stretch, IR, but then Fisher proposed it on the basis of other measurements and all that. Okay. Now, why did they get the Nobel Prize and not the Woodward? The possibility is that, or the explanation is that Fisher and Wilkinson developed this organometallic chemistry out of this ferrocene. Instead of ferrocene, they Fisher prepared the dibenzene chromine. and many other things which are analogous to that one, and hence a huge amount of work was done in organometallic chemistry, not synthetically, it's also application oriented thing, and because of that one those two people got the Nobel Prize. And then between Fisher and Wilkinson there was always a fighting. They divided the periodic table, but then the students won't listen, they will trespassing with each other, all those things were happened. Fisher was upset when Wilkinson and his German speaking co-worker F.A. Cotton's book, I think all of you know about it, they wrote a paper in German also. And then Wilkinson to Rosenblum was a student of Woodward. Okay, from Woodward, he asked, okay, Wilkinson was very unhappy with him, saying that why do you want ruthenium chloride? Because they wanted to prepare the ruthenium analog of that one. And then as I told you before, Woodward also wrote to the Nobel Committee and all that. Okay, but then nothing happened, only these two people got the Nobel Prize, Wilkinson and Fisher, and not Woodward for that one. And Woodward, what he wrote here, both of these concepts, this unusual sandwich structure and prediction that such structures would display unusual aromatic characteristics, both these concepts were simply, completely and entirely mine, and mine alone. This is what Woodward wrote, but they didn't bother. They didn't give him the Nobel Prize for that one. Okay. And then these things I will not go into the details of that one, because I just wanted to tell you something about ferrocene and all that. I will perhaps go to this one. Okay. No, these things I will leave out. Okay, because I think that I had to leave some time for the questions. Okay, and this is perhaps the last slide. And I did not tell you anything about my research work and all that. This is part of my research work, just one slide for the sake of showing it, that's all. Okay, overall what I wanted to tell you is that there are a large number of discoveries, not in chemistry, okay, in all sorts of science and all that. The only thing that we have to know about is when we observe something unusual, this is for the younger generation, when we observe something unusual, what you have to do, you have to try to analyze that one. You should know the significance of this particular observation. Now, the thing is that this as far as the organometallics is concerned, Prussian, okay, he sent that paper to Nature, whereas the other three papers sent it to Journal of this one Chemical Society. Okay, because they knew that it was different, but then they did not understand the significance of that particular compound to that extent. The reason being that they were unhappy that the iron compound they got was not able to catalyze the reactions they wanted to do. So they just lost interest. They just wanted to publish it. But this Prussian knew that there was something really very, very unusual about this particular compound. He sent it to Nature and he got a good publication. The unfortunate thing for him is that he didn't extend that one because he was not having a permanent position, and they didn't recognize his work as far as the Nobel Prize is concerned. But then his publication got in Nature, the other people, this one, they publish in the Journal of Chemical Society. This kind of a thing happens to many of us, I think, those people who are well versed with publications and all that. Okay, thank you all.
Thank you, Professor Kumara, for an excellent talk on the discovery of Prussian and its Prussian blue and its users. So, open to a couple of questions.
It's actually a very good talk, and this Prussian blue is replaced by the bimetallic like bismuth or some other.
Yeah.
So, what the main reason for the color in this case actually?
In the other cases and all that. In the bismuth case, it's a little bit difficult to say because bismuth has two oxidation states, bismuth 3 and bismuth 5. But the color variation, I think that there may be some other reason also. Although in those cases, bismuth 3, I don't think that it will go to bismuth 5. For bismuth, the normal oxidation state that we know, bismuth 5 is known, lot of work is there, but then I don't think that gets oxidized or something like that. So, the bismuth 3 could act like this iron 3, that is a possibility. Okay. But then bismuth 3 has other features and all that. Now, many of you may know about the perovskites and other things. That is something that I am not aware of that. Bismuth based perovskites, they have some other interesting features. There is a lone pair over there on bismuth.
If there are no questions, let us thank, join me thanking Professor Kumara.